Video is just a quick overview of thermodynamic potentials and Maxwell relations. I begin by reminding you what the natural variables of energy and entropy are, and I remind you about the fundamental identity. And then I go through and show you how you can use this to define conjugate variables. S and T are conjugate, V and P are conjugate, mu and N are conjugate. And then I show you how to derive Maxwell relations. On the next slide, I introduce more potentials, and I do similar sorts of things. I remind you what the natural variables are. I show you how to get to Maxwell relations, at least some of them, and we reiterate the facts about conjugate variables and what the natural variables are. Then we get some applications, and we consider a pure substance, and the first thing I do is derive the second TdS equation, because we derived the first TdS equation in class. Then I equate the first and second TdS equations, and I go through and calculate a new result, which is sometimes called the heat capacity equation. But anyway, I need to put it in a slightly different form using the properties of partial derivatives. And so we make that calculation, and we get an expression for Cp minus Cv. And note that one of the things we can show from this is that Cp is never less than Cv, although my handwriting mangled that, so I put an overlay on there to explain that properly. And the basic point, though, is dp by dv at constant t is a necessarily negative function. Temperature is going to be positive. The square of that other derivative is clearly going to be positive. So what that means is that Cp minus Cv can never be negative, and then we deduce a variety of results from it. Then I go through and do some more calculations in terms of volume expansivity and the coefficient of isothermal compressibility. And then I deduce the second energy equation for you. Again, we deduce number 1 in class. And then I derive both versions of the Gibbs-Helmholtz equation, giving you actually two derivations of the second part of it, the usual one on the next page, and a somewhat simpler one on the bottom half of this page. To some extent, it prefers whether you, it depends on whether you prefer to do physics or mathematics. The derivation of the one with t squared in it on the bottom half of this page uses physics. The derivation on the next page, this one, simply uses mathematical properties. Most people don't like this derivation, or many people don't, but it is the one that's in almost every textbook. So that's it. I'll see you on a Zoom meeting sometime soon. Have a good weekend.